So we are discussing, now we will be discussing this one, magnetism. And we thought for a while that when there is magnetism, it is completely, no, it is completely separate, different, no, from the word electricity. But somehow, no, there's the term that they coined, no, electromagnetism, that eventually, no, makes us think that magnetism and electricity are basically, no, not that separate as a concept. So somehow, no, they have a connection. No? So how or in what way are they connected? No? So maybe as we discuss that topic, no, we will come to realize it in here. No? So who were the very first people who were very much fascinated with magnetism? Probably. No? So maybe we can begin there, no, as our point of discussion also. And one of the most curious individuals, now which we already learned from our discussion on electricity and electric charges, we realized that in the ancient time, there were these groups of people who were really not scientifically inclined. They are so fascinated about their environment, phenomena that they observe in nature. No? And these are the Greeks, no? And they uh, they happen to observe this thing that they probably call as magnetism. No? That's our present term today. No? But let's take up, no, this thing about magnetism. Now we have a brief history now of magnetism. So we have names like William Gilbert. No? So Gilbert, no, probably studies about magnetic materials, no? Like compasses, the Earth's magnetic field. No? So the Earth is one huge natural magnet. So we can know that it is magnetic, no, by putting, no, a certain gadget like a compass, and we will realize that that compass behave, no, in a very specific manner. No? And how does it behave is relative to the Earth. No? So there's always this direction in the Earth where that compass is always pointing into. And if the compass is a magnetic material, why does it follow, no, a certain specific direction in the Earth? No? So those are things that will make us no wonder or relate, no, that the Earth is also some kind of a magnet. No? If a magnet is affected by the Earth, then the Earth must be, no, a magnet itself. Now in 1820, no, there's also another guy, Mr. Hans Christian Ørsted, finds that electric currents deflects a compass needle. No? Now, an electric current, no, if we look at the work of Ørsted, an electric current, there's no magnet there. No? If you have a wire and that wire, no, is carrying some amounts of letter I, which we call as the current, some number of amperes, they observe that the compass needle is also, no, deflected or is affected by this electric current. No? So somehow, no, that's one big observation probably that Christian Ørsted, no, discovered, no, or noted in his studies. Now another individual, Andre Ampere, no? So Andre Marie Ampere finds that parallel wires carrying current produce forces on each other. No? So if you have a parallel wire, no? Two wires that move, no, in line with each other, like the one that you see in the pole of street lights, no, or the electric pole streets. There's always these pairs of wires, or maybe two or three wires, no, that are made to hang there, and they are parallel to each other. No? Now, why are they separated from each other? Somehow, no, if they are not, probably they will try to, no, attract each other, and that's what Andre Ampere, no, noticed, no, when he found that if there are two wires that are side by side, no, they're either pushing each other away or maybe attracting each other towards each wire. No? So observations of uh, of Ampere and Orsted probably may have some kind of a similarity. Now in the 1820s, 1830s, we have another famous guy, Michael Faraday, develops the concept of the electric field and shows that electric current plus magnetism eventually creates some kind of a motion. So we call that as, or he calls that as the motor effect. So if we are dealing with motors, basically, we we see there that there is now a force that is created now inside our electric motor, and that's the cause. That's the reason why the electric motor turns or spins. No? So if there's a force there, and the force turns about a certain distance, and then you create a torque. No? So there's always a torque, a turning motion there in our electric motor. No? So depending on how or where you apply it, no, then there is a certain strength to that force. So if you use it as a water pump, then it must be very, very powerful, no, so that the water will be drawn out. If it's not really that, uh, it does not really need that much strength, no, then maybe you can just use it for electric fans, no, and some light jumps. No? And we have this famous guy, and I wanted to remember his name. His name will come out now in our future discussion, maybe in the discussion in light. No, his name will still come out. So he is not as famous as Albert Einstein, but James Clerk Maxwell is one very very intelligent guy. No? He's an intelligent, very talented person, and he was able to create this grand theory. No? He combines many other theories and then pack it into one single equation. No? He has this mathematical equation that explains electricity, magnetism, and even the concept of light, no? in that sense. No? So he's not really as famous as Albert Einstein, but no, he may be he may influence also the work of Einstein. No? Why Einstein came about with his other theories. So electromagnetism. No? Now, the Greeks were the very first ones who were probably able to discover these uh, stones, rocks. No? They travel a lot, and because of that one, they step on some stones, and these stones will eventually disorient or reorient. No? Kaya nasa daan mo sila sa dalan. You step on them, and then therefore they get dislodged, and disoriented. And then, however, without anybody touching them, they will always go back to their original position. No? Now, the Greeks who happened to step or onto uh, tumble on these rocks, tiny rocks, and were able to dislodge or made them move in a certain direction. But eventually, when they return, they discovered that these rocks always return to their original shape or original position. That they kind of wonder over a period of time, why do these stones behave that way? That even without people touching them, they always align themselves in a particular manner. Now, these traveling Greeks discovered this stones that has some kind of a force in Asia Minor. No? So they travel in this place called Asia Minor, which is today's present Turkey. Now there's a specific place there that they call Magnesia, where they found these stones. No? And today I think we call them as lodestone, but the place where they were discovered was Magnesia. And because of that, the word magnet also was born because of that place called Magnesia. Now, these lodestones attracted iron filings. No? So these are natural magnets, guys. And when you put um, some kind of sand, and that sand probably has a mixture of very tiny metals. Now, when you put the lodestone with those iron filings or with those sand, no, they kind of attracted, no, they get attracted to the lodestone and then they will follow the lodestone. Especially if you put the sand, no, on top of a piece of paper, no, and then underneath the paper you put a lodestone there, then the iron filings or the sand is now attracted to the lodestone. Lodestone seems to attract each other as well. No? So if you put two of them, no, in a particular uh, direction, of course, no, not in just any manner. So they kind of attract or maybe they repel each other. And eventually they were the ones who were used as a compass. So one end always pointed north. No? So our compass will always, no, have one specific direction as pointed by the arrow of your compass. A lodestone again is a kind of a natural magnet. The same way as the Earth is also a natural magnet. Now we have several kinds of magnetic materials. Now, number one of these materials, these are called as the paramagnetic materials. And what are paramagnetic materials? They are not, no, strongly attracted to a magnet. No? So they don't attract, no? They don't get attracted, no, to magnets. Like example, there aluminum. So if you put a magnet aluminum, you will barely see, no, the aluminum being, no, being disturbed by the presence of a magnet. No? In magnesium. Now the relative permeability. Now permeability, I think, is the ability of the material to absorb, no, to absorb some kind of magnetism. So they have a very small permeability. No? So aluminum, tin, magnesium, they have small, no, but still a positive, no, permeability. So permeability is something, no, if you will consider a material is permeable to water, then water is able to pass through it. No? Maybe other materials is not able to pass through the material, but permeability, no, of a material to water will only permit water to move or get into the material. Now, another type of magnetic material is our diamagnetic. Yeah? Diamagnetic are the ones which are repelled. No? So if there's a magnet, then they will move away. No? So some metals like zinc, mercury, lead, sulfur, copper, uh, silver, bismuth, no? And wood. No? They are observed, no, at one point to move away, no, in the presence of a magnet. No? Now their permeability is slightly less than 1, no? Very small. And these are the values of our permeability. No? Now the third one, which is the material that is strongly attracted to a magnetic field or magnet, is known as ferromagnetic. Now the word ferro or ferrous, ferric, no? We always use that, no, in materials that contains iron. Iron is not symbolized as I in the table of elements, but it is symbolized as Fe. No? Fe stands for iron. And materials that have iron, you have steel. No? Steel, no, is a mixture of iron and some other metal. No? And eventually, no, you end up with a steel, no? A very strong metal. No? Nickel, cobalt. No? So they have permeability that are very, very high. No? So meaning they can absorb more magnetism. No? So permeability speaks of its ability, no, to let, no, magnetism pass through it. Now, permeability is a property of a material that describes the ease, no, with which magnetic flux is established in the component. No? So if you have a metal, that's your component material. Then if it's able to absorb magnetism, then it is a very permeable material. Now, materials may possibly allow magnetism to go through it, but the amount of magnetism that possibly remains, or how much you can make it into a magnetic material from not magnetic, is termed as retentivity. How does it hold the magnetism that it receives or absorbs? So that's another factor in how you can magnetize a material. By the way, how important are magnets? Kung kababi maglantaw, what do you think are features or importance of magnets? Joshua,
Sa speaker, sir.
ano ha?
Sa mga sound
Sound,
speakers.
sa speaker, correct?
Mm.
So we always have that. Another example pa. Joshua, another example. Aside sa loudspeaker,
May ref, sir, may dyan.
Para nga magsira ang portahan niya, So the door of the
Ref.
refrigerator closes, So we have ref magnets, Okay? So kung travel man ka mo sa lain nga lugar, meron man kita nga ref magnet man tawag nato, But we are referring to the ref magnet, manaya ang ating souvenir, that we place on the door of our refrigerator, So, but that's another one. Who else? Si Ruel. Ruel, can you give us another use of magnetism? Mr. Celebria. Sir Celebria.
Wait lang, sir.
Before tayo makadto kay Mr. Celebria, Miss De La Torre, how about another example of the use of magnetism? Miss Cecilia De La Torre.